Section 3.5, the graph of rational functions. So the graph of a rational function, how should we approach it? Well, here's the deal. We should factor everything and we should figure out the domain. Now remember that the domain is going to come from the denominator initially. But once we simplify, then we're going to get vertical asymptotes and holes from the domain and what simplifies. Next thing we should do is we should find any horizontal asymptotes, which of course will rule out oblique asymptotes, or if we have oblique asymptotes, find them, which of course will rule out horizontal asymptotes. Next, we should find the x-intercepts. Now essentially you just set the equation equal to 0, but because it's a rational expression, you then multiply both sides by the denominator, and then you're really just setting the numerator equal to 0. That's what happens. Then we should find the y-intercept, which is of course plug in 0 to the simplified equation. Then we should graph it. Now to graph it, what are we going to do? We should of course look for the vertical and horizontal asymptotes or oblique asymptotes. Look for the holes. Those are usually going to be dead giveaways. Then if you need to get a better picture, you should pick extra values that aren't domain restrictions to try to get the graph correct. R of x is equal to x plus 5 divided by x times x plus 17. So step 1, let's figure out the domain. Well, of course, for the domain, we know we take the denominator and we say, oh, well, it can't be equal to 0. So x times x plus 17 cannot equal 0. Then we get the zero product property, that is x cannot be equal to 0, and x plus 17 cannot be equal to 0. And so we get that x cannot be 0 and x cannot be negative 17, so our domain is going to be from negative infinity up to negative 17, excluding, union, excluding negative 17, up to 0, excluding 0, union, excluding 0, up to infinity. So now we have the domain. Next we want to find the vertical asymptotes. So to find vertical asymptotes we should look at our rational expression and figure out will it simplify. This is completely factored, and so x plus 5, x plus 17, the x, there's no simplification that's going to occur, which then forces any of the domain restrictions that we had to be vertical asymptotes. And so specifically, this is going to give me two vertical asymptotes, one at x is equal to negative 17, and one at x is equal to 0. So two vertical asymptotes. Then we have to have the discussion about horizontal asymptotes. So let's look at our degrees in the numerator and the denominator. But notice that the leading term in the denominator is x times x, or x squared. That means that the denominator has the larger degree. And since the denominator has the larger degree, then we do have a horizontal asymptote, specifically at y equals 0. Remember, if the denominator's degree is larger than the numerator, automatically y equals 0 is our horizontal asymptote. Next, we want to find our x-intercepts, but to find the x-intercepts, just set the numerator equal to 0. That is, x plus 5 is equal to 0, minus 5 minus 5, x is equal to negative 5. So now we get the x-intercepts being negative 5, 0. That's the only one. Then we find the y-intercepts. Well, the y-intercepts are just found by taking and plugging in 0 into the equation. That's going to be 0 plus 5 divided by 0 times 0 plus 17. But notice, and we should have known this before, that is, 0 is not in the domain of this function. So there are no y-intercepts. Then we should use all this information and see what we get. Well, of course, the vertical asymptotes and the horizontal asymptotes are probably the easiest place to start. And so I'm going to extend this a little bit. And let's say that this is negative 17. Then we get a vertical asymptote at negative 17. We also got a vertical asymptote at x equals 0. So that's going to actually be the y-axis. We also get a horizontal asymptote, that is y equals 0, so that's the x-axis. Then we can plot the ordered pairs that we found. So the ordered pairs that we found were the x-intercepts. There was no y-intercept, so our x-intercept is negative 5, 0. And just to make an argument, we found the x-intercept earlier, but we didn't discuss its multiplicity. Well, what is its multiplicity? It's 1, right? X plus 5 only shows up one time as the factor, which means that it's a crossing. Odd multiplicity means it's a crossing. So keep this in mind. We have a crossing. Then what else do we know? Well, now we don't really know exactly what this graph looks like. But we do know that more or less we have to approach all these asymptotes. And so how can we get a better representation? Well, essentially, we can just plug in values. And so let's say we plug in something to the left of negative 17. How about we plug in negative 18? Well, r of negative 18 is going to be negative 18 plus 5 divided by negative 18 times negative 18 plus 17. That's then going to give us negative 13 divided by positive 18. But what matters here is that I know it's below the x-axis. And since there are no x-intercepts over here, I can actually fill in what this looks like. I guarantee it looks like this. It has to approach that horizontal asymptote. It has to approach the vertical asymptote. And since there's no x-intercept over there, it never crosses. I say we can do the same thing over here on the right. How about we plug in 1? And so if I plug in positive 1, then we're going to get 1 plus 5, 1 times 1 plus 17. That's going to give me 6 divided by 1 plus 17 is 18. 18 times 1 is 18. And that does reduce to 1/3. But what matters here is that it's positive. And so really, I know that this part must be above the x-axis and approach the horizontal and vertical asymptote. Now remember, I know that it will never cross a vertical asymptote, but it does approach the horizontal asymptote and it does approach the vertical asymptote, so it must look like this in some form or fashion. It's not perfectly to scale, I'm just trying to sketch it. Next, we've got to worry about what happens in the middle. Well, notice that this is a crossing. And since this is a crossing, I claim that really we could either find some value over here, see if it's negative or positive, and then we have completed the entirety of this graph. We just need one more value. So why don't we plug in negative 1? That'll be easy for us to change. Negative 1. Negative 1 plus 5 is going to be 4. And then negative 1 plus 17 is positive 16. Made negative is negative 16. That's really going to be negative 1/4. So that is, at negative 1, I've got negative 1/4. And so now I actually know what this looks like. Well, it has to approach this asymptote. Since it has to approach the vertical asymptote, it approaches down here. It does have to pass through this point. Then it crosses through the x-intercept. And it has to approach the vertical asymptote. Once again, I make no claims that this is a perfect representation. All we really care about is a pretty close sketch. And I claim that, although it's a little rough looking, it's a pretty close sketch. Let's do the same thing. Step 1, let's find the domain. Well, we know that x plus 8 cannot equal 0. So that is x cannot equal 8, negative 8. So that is the domain is from negative infinity up to negative 8, excluding union, excluding negative 8, up to positive infinity. Then we need to reduce this function. So two numbers that multiply together to give me 56, but sum together to give me 15. Those are 7 and 8. So this is actually equal to x plus 7 times x plus 8, all divided by x plus 8. All right, this is a little strange, because now what happens? Well, what happens is x plus 8 divided by x plus 8 is 1, and we're left with just the function x plus 7. But remember that our domain kicked out negative 8. All right, so a few things happen. First off, what are the vertical asymptotes? Well, there are none. Because when we reduce this rational expression, there are no more restrictions in the reduced denominator, there's no vertical asymptotes. But there is what's called a hole. And specifically, that hole is at that domain restriction. It's going to be at x is equal to negative 8. Well, but now I want to know exactly where the hole is, so just plug it into here. Negative 8 plus 7, or r of negative 8, is going to be equal to negative 8 plus 7. Now, this doesn't actually make any sense because it's a domain restriction, but it does give us a value of negative 1. And so at negative 8, we get the ordered pair, negative 8, negative 1. And so I know that there's a hole specifically at the value negative 8, negative 1. I'm erasing this because, once again, it doesn't make any sense. Well, honestly, if we want, we could go ahead and mark that. At negative 8, negative 1, there's a hole. I'm just going to put an open circle. That value does not exist. Then we want to talk about horizontal asymptotes and oblique asymptotes. But when we look at the reduced rational expression, there's no degree arguments in the numerator or the denominator because there is no denominator, and so they're neither horizontal asymptote or oblique asymptote. Then we want to find the x-intercept, but to find the x-intercept, just set this equation equal to 0. X plus 7 is equal to 0. We get that x is equal to negative 7. Then we get the x-intercept is negative 7, 0. Then if I plug in 0 to this equation, 0 plus 7 is 7, and so we get the y-intercept of 0, 7. And so now I get those other ordered pairs I can plot, negative 7, 0, and 0, 7, and then we graph this. But notice that this is really the polynomial r of x is equal to x plus 7. That's just a linear function. So it looks like a line, where specifically there's a hole at the negative 8, negative 1. And that's the graph of this rational expression. Let's do it again. Step 1, domain restrictions. So we know that x plus 5 cannot equal 0. That is, x cannot equal negative 5. So the domain is from negative infinity up to negative 5 excluding negative 5 up to positive infinity. Then we should reduce this rational expression by factoring. And so x squared minus 3x minus 4, two numbers that multiply to give us negative 4 but sum to give us negative 3. That is negative 4 and positive 1. So I get x plus 1 times x minus 4, all divided by x plus 5. At this point, we check to see if there's any reduction possible, but there's not. And so now I know that my vertical asymptotes are explicitly my domain restriction. And so that is x is equal to negative 5. We get a vertical asymptote. Next, we have to deal with horizontal asymptote or oblique asymptote. Well, degree arguments. The numerator has a higher degree, which specifically means there is no horizontal asymptote. Then notice that the degree of the numerator is 2, the degree of the denominator is 1. That tells us explicitly that we do have an oblique asymptote. Remember, if we have a degree difference of 1 larger on the top, then we have an oblique asymptote. So let's find that oblique asymptote. Remember, we do division, and personally I'm going to use synthetic. So negative 5 is the 0, and the coefficients are 1, negative 3, negative 4. Bring down that 1. Negative 5 times 1 is negative 5. Negative 3 minus 5 is negative 8. We do end up getting a remainder, but remember that for this argument, the oblique asymptote, we don't need the remainder. So I'm just going to stop, not waste my time. That is, y is equal to x minus 8. So now I know specifically that my oblique asymptote is the dashed line y equals x minus 8. Then to find the x-intercepts, I set the numerator equal to 0. So that is x plus 1 times x minus 4 is equal to 0. 0 product property, x plus 1 is equal to 0. X minus 4 is equal to 0. Then I get that x is equal to negative 1 and x is equal to positive 4. And so my x-intercepts are the ordered pairs, negative 1, 0 and 4, 0. Then to find the y-intercept, that is r of 0. R of 0, I'm going to go back to this initial one because the reduced and the initial were the same, and that's a little easier to calculate for this because then it's 0 squared minus 3 times 0 minus 4 divided by 0 plus 5, which is just going to be negative 4/5. And so I have a y-intercept at negative 4/5. Of course, watch out because sometimes you'll answer as ordered pairs and sometimes you'll answer as the integer or the rational. So now let's consider the graph. So if you have your printout, you can see that I have some graphs for you. So let's look at what the graphs look like. Well, let's start by finding the vertical asymptotes and the oblique asymptote because that will probably make life easier. Specifically, the vertical asymptote has to be at negative 5. Notice that the vertical asymptote and the oblique asymptote for all 4 of these images is the same. And so at this point, I'm already off to a start and I can't rule anything out yet. The next thing is let's use all the information we found earlier. Let's find the x-intercepts and the y-intercepts and see which one of these has them. So we know that the x-intercepts are 4 and negative 1. And so 4 and negative 1, at this point, I can rule out this one and this one. But then the top 2 are possibilities. All right, well, what else do we know? Well, honestly, at this point, I see that this has an x-intercept to the left of negative 5. And since that's an x-intercept to the left of -5 and I didn't have one of those, this one can't be it. That's not possible. And so just based on the information we have, I'm going to choose this one. Now, let's say that we didn't have enough information to distinguish between the two. How would we get a better representation? We would have to pick some x values, plug them into the function, and see what we get to find a better representation. But in general, follow the steps we just did. Horizontal, vertical, or oblique asymptotes, find those first. Then look at the x and y intercepts, rule out everything you can. At that point, then you may have to pick more points to plug in to check it. But now let's do something in the opposite direction. Given this rational expression, or rather this rational function graph, let's actually come up with an equation. All right, so let's notice some things. So we have a vertical asymptote here and here. What does that mean? Well, that means that we have domain restrictions and we have things happening at -5 and +5. So I know that for the domain, x can explicitly not equal 5 or -5 because of those vertical asymptotes, which also tells me that my denominator must have those factors in it. That is, x minus 5 and x minus minus 5, or x plus 5. Okay, great. So the vertical asymptotes have told me what my denominator must have in it. It may need more, we'll see how this goes, but it's got to have those things. Next, let's look at our horizontal asymptote. All right, so we have a horizontal asymptote. Specifically, that horizontal asymptote is y is equal to -3. Well, then we have to think about when do we get horizontal asymptotes that aren't at 0. Specifically, that's when the degree of the numerator is equal to the degree of the denominator. So this actually tells us that the degree of the numerator equals the degree of the denominator. Now, since that's the case, I do see that I know my denominator is going to be degree 2. And if it's going to be degree 2, then my numerator is going to have to be the same degree. But what else can we use to find the correct numerator? X-intercepts. All right, so let's see if we have any x-intercepts. Well, we do have one, right? We have this right here. We have 0, 0. Well, if 0 is the x-intercept, that means that specifically, since the x-intercept is 0, that means that the numerator has the factor x minus 0 or just x. All right, great. So let's write down the things we absolutely know right now. My function has to have a matching degree in numerator and denominator, and it has to have the ratio of leading coefficients equaling -3. And remember, that's because if the degrees are equal on top and bottom, that's the only way we get y equals some number that's not 0, and it's not oblique. And so my first thought is it's really going to be -3/1 because that would be the easiest. It may be more complicated than that, or possibly could be, but let's go with easiest right now, -3/1. All right, so let's fill in what we've got. I know that this thing has to have x plus 5 and x minus 5 in the denominator. That's our vertical asymptote step. Then it has to have a 0, a factor of x, in the numerator. But the degrees have to match, and so it's okay for this to be raised to a higher power. But something we didn't discuss is that technically this is a bounce, or a touch, which means that the multiplicity of the 0 must be even. Must be. It's got to. Because that's what multiplicity tells us. It tells us if zeros are bounces or crossings. And so since we have a bounce or a touch here, then I must have an even multiplicity. And since I see my denominator is squared, and I need the degrees to match on the numerator and the denominator, I'll just make this squared also. Then the only thing left is the ratio of leading coefficients must be -3/1. Well, if that's the case, let's just write that, -3, 1. And the truth is at this point, without simplification, I now have a function for the rational expression of the graph that we see.